the cloud button. Recording in
Okay.
progress.
So now we are recording. So it is now 15:00 Istanbul local time, and I believe it is 7:00 Cleveland local time.
That's right.
So maybe uh, I will introduce Professor Nick Gurski to the audience. He is professor at uh, Car- uh, uh, Case Western Reserve University in Cleveland, and he will going to talk on what. If you share the screen, I will read
Oh,
the
right.
title.
Yeah, I was, that's right. Here we go. Aha, there we are.
Yeah, computing with symmetric monoidal functors, and it is great pleasure to have Nick here. He is one of the big experts in higher category theory, and yeah, I leave the word to Nick. Yeah, thank you.
Well, thank you very much for that introduction, and thank you for the invitation. It's a real pleasure to be here. I don't give many talks at 7 a.m. And I don't know, it's kind of invigorating. So I'm enjoying this. Um, this is a joint project with Niles Johnson, um, roughly as part of our long-term investigation into symmetric monoidal structures, higher Picard categories, and the relationships to stable homotopy theory. So we're going to start with some audience interaction. So you have a 3-question pop quiz. These are not meant to be trick questions. So they're all of the form, does this diagram commute? So here we'll start with 4 topological spaces, and I've taken various Cartesian products and kind of swapped coordinates around. So if you want to like maybe put your little hand up on the Zoom thing, if you think uh, this diagram commutes, I don't know if there's like a thumbs down or something if you think it doesn't commute, but go ahead, take a. Anybody want to? Okay, I've got one. I've got a couple thumbs up. So the answer here is yes. And like I said, it's not a trick question. Essentially, if you start with a point in the common source of these 2 morphisms, so you might write that as XYZW now with small letters instead of capital letters for the spaces, then when you trace them both around, the y coordinate both ways is in the space y. So it's always going to be the first coordinate, no matter if you do it as this composite of 3 permutations or just straight across. In other words, I designed this diagram so that you could just look at it and know that you didn't have to do anything to conclude that it commuted. So if we make things slightly more difficult, now we've just got X, and so I've still got a product of 4 spaces, and a variety of permutations, but it's not as clear if this diagram is going to commute or not, because you don't have a sort of obvious indication of where the coordinates go. So does this one commute?
I have a guess.
Okay,
Maybe.
go ahead.
I don't think so because in the upper path you swap 2 and 3, and then you swap 2 to 4 again. So I think that might not be commuting, but I'm not sure if this is because of the category of topological spaces.
Right. So there's nothing actually specific about topological spaces in this example. I wanted to just pick something familiar, but you're right. It doesn't commute. So this is fundamentally just a question about, is one element of the symmetric group S4 equal to a different element? So if I wrote a point in the common source as x1, x2, x3, x4, and trace around these two ways, then you'll get two different answers. And you can see that by just tracing where the indices go. So if I go along the top three composites, you get x3, x1, x4, x2. Whereas if I go straight across along the bottom, you get x2, x1, x4, x3. So not only do some of the coordinates differ, most of them in fact do. So this one doesn't commute, even though it's a diagram just made out of the symmetric monoidal structure. Okay, last one. So now we're gonna once again start with the topological space. And here I'm gonna take homology with coefficients in a field, so we don't have to worry about any kind of Tor sort of issues, anything like that. There's nothing complicated going on. And look at this diagram of various homologies. So the maps that I've marked as EZ are Eilenberg-Zilber maps. So those are going to take the homology, tensor homology, and represent classes there as homology in the Cartesian product. And then we've also got a variety of symmetries. So this one is obviously a bit more complicated because you've got to think, how do these Eilenberg-Zilber maps interact with these permutations? And does it matter if I do the permutation before or after I've kind of put things inside homology? So I won't try to get you to actually do this. But the answer here is yes, this diagram does commute. But you'd have to combine some knowledge of the Eilenberg-Zilber maps with a computation in the symmetric group to be able to conclude that this commutes. So in a lot of ways, the goal of this talk is to try to give you a simpler way to look at a diagram like this and not do most of that work. And that's the whole point of a coherence theorem. So a coherence theorem could take a lot of forms, but I like to think of a coherence theorem as a thing that tries to do most of a computation for you. So an example of a coherence theorem is the famous coherence theorems of Maclane on monoidal structures. So in a monoidal category, people say that every diagram of associativity and unit isomorphisms commutes. So if I make a diagram and it's just made out of reassociating tensor products and putting in or taking away unit objects, then that'll commute. Similarly, in a symmetric monoidal category, I can do associativity and unit isomorphisms, but also symmetries. And the relevant coherence theorem there is that one of those is going to commute if, when you compute the underlying permutations of the morphisms in your diagram, you get the same answer. So this is going back to just doing a computation in the symmetric group, comparing one element with another element, trying to decide if they're the same. So, as I said, this is joint work with Niles Johnson, and we're interested in these kinds of diagrammatic coherence theorems, specifically related to functors between, in our case, symmetric monoidal categories. Those are the things that we kind of started this project with. And this is refining a method that I learned from Joyal and Street in their braided tensor categories paper quite a long time ago, but it doesn't really seem like this method has appeared more widely. So here's an outline of what I'll be talking about. First, I'm going to have a kind of quick refresher on symmetric monoidal categories and symmetric monoidal functors. This is fundamentally a kind of talk about two categories and two monads. So I will give you a little refresher, hopefully, on how those things work. And then we're going to talk about this method originally due to Joyal and Street, And then we're going to get back to some symmetric monoidal categories and talk about some examples. So here is a very abbreviated definition of a symmetric monoidal category. Consists of a category M together with a tensor product that I will write as a tensor, and a unit object that I'll write as 1. Then the monoidal part comes with 3 natural isomorphisms, an associator from X tensor Y tensor Z to X tensor Y tensor Z, left and right unit isomorphisms between 1 tensor X and X or X tensor 1 and X. And then the symmetric part, which is also an isomorphism in a just a braided structure, would be this beta, an isomorphism from X tensor Y to Y tensor X. And we need 3 kinds of axioms. So there's a MacLane pentagon for associativity and a triangle relating the associator with the units. That'll give you just a plain monoidal category. There's a symmetry axiom for 3 objects and 1 for an object in a unit. And if stated correctly, maybe you need to throw in 2 symmetry axioms here. This would actually give you a braided structure. And then to say that it's symmetric is to say that if you do the symmetry twice, you get the identity. So this is the kind of basic object that I'm going to be interested in working with. And there are always maps between objects of interest. In this case, I'm going to be thinking about symmetric monoidal functors. So a symmetric monoidal functor from M to N is a functor together with 2 different natural isomorphisms. F2, which relates the tensor product after applying the functor to each of the variables, to F applied to the tensor product. So you can think about this as sort of putting the tensor product inside the functor. And then there's an F0, which relates the unit object in the target N. S here is the unit object for N, with the image of the unit object from M. And we need 2 kinds of axioms. So the first is going to tell us that we've just got a monoidal functor. Those are going to be some axioms relating the associativity left and right units with these isomorphisms F2 and F0. And then finally, we need an axiom that tells us how the functor interacts with the braiding or the symmetry. And so that's the only one that I've drawn out. So if you take F dot fx dot fy, you can either put the tensor inside the F and then braid in the source, or you can braid in the target and then put the tensor inside the F. And that'll give you 2 different morphisms from fx dot fy to f of y tensor x. And that has to commute. Okay, so examples are lots of familiar things. So any category that has products or coproducts, so category of sets or topological spaces, vector spaces, category of, say, small categories, all of those are symmetric monoidal under either the product or the coproduct. Algebraic type examples like categories of modules or vector spaces using the tensor product. Or if you want graded or differential graded versions of these kinds of things with appropriately adjusted tensor products. The motivation for this project actually really comes from trying to understand the higher dimensional analog of the monoidal structure on the category of chain complexes of abelian groups. So Niles and I were interested in taking abelian groups and promoting those to Picard categories, which are symmetric monoidal categories where all the objects and morphisms are invertible. And we wanted an analog of the usual tensor product of chain complexes with the standard sign rule. The free symmetric monoidal category on one object is equivalent to the disjoint union of all the symmetric groups. So BSN is the category with a single object and then an automorphism group of Sn. And if you take the disjoint union of all those, you'll get another groupoid. And that thing has a natural monoidal structure where you just do addition of natural numbers on the objects. You think that Sn is the automorphisms of the object n. And this is not quite the free symmetric monoidal category because this one has strict associativity and unit conditions, but this is equivalent to it. If you want the non-strict version, you can do something just slightly fancier, but not very much. I point this out because we're going to be doing a lot of free things in a little while. So what about symmetric monoidal functors? If you've got a functor that preserves products or coproducts, that will automatically be a symmetric monoidal functor between those categories. Also, the usual isomorphism showing that tensor distributes over sum is an instance of a symmetric monoidal functor. Here, the functor is R tensor blank. And so you can see that you've got R tensor blank applied to A plus R tensor blank applied to B on the left, and then R tensor blank applied to A plus B on the right. So here the symmetric monoidal structure is given by plus, and the functor is actually given by tensoring on the left. So these are the two main styles of coherence theorem that you often see when people discuss monoidal categories or something similar. So the first is a kind of strictification theorem. Every monoidal category is equivalent to a strict one. That's one in which the isomorphisms A, L, and R are identity morphisms. This is usually the kind of theorem you use if you want to just pretend the associativity and unit isomorphisms aren't there. You say, well, okay, I've got the Cartesian product, and it's not true that if I take the product of three things with one association, it's equal to the product using the other association, but I'll just replace my, say, category of sets with Cartesian product with an equivalent monoidal structure that's strict. And then the second one, which is really the topic that I'm interested in today, is this kind of theorem that says that every diagram in a monoidal category commutes. That's got a little asterisk because it's not true. So it's only true. It's not true. Yeah, it's only true in the case of free monoidal categories. And the correct statement is that if you've got a diagram of associativity and unit constraints that lifts to a free diagram, a free monoidal category, then that commutes. It turns out that it's hard to come up with examples that don't commute, but you can come up with some degenerate ones. A fun example of a symmetric monoidal category that has some kind of degeneracy to it is if you take the category of countable sets under Cartesian product, they're all isomorphic to one another, and you just have to go around kind of picking some slightly strange things. And once you've started picking strange isomorphisms between countable sets, it's not so surprising that you can make a diagram that doesn't commute. So this is exactly the kind of issue that almost never comes up when you're dealing with a monoidal category that you find in nature. So the symmetric version is very similar. The first of these theorems, that every monoidal category is equivalent to a strict one, you can just say the same thing. Every symmetric monoidal category is equivalent to a symmetric monoidal category in which the underlying monoidal structure is strict. You're not allowed to replace the symmetry with an identity, but you are allowed to replace the associativity and unit isomorphisms with identities. And then the second theorem is no longer true, but we have a kind of further condition that a diagram in a free symmetric monoidal category will commute if and only if the legs of the diagram all have the same underlying permutation. So this is an additional condition that you need in the symmetric case. And this shows that it matters what structure you're dealing with, and you do have to adjust your coherence theorems. Oh no, what happened? Oh no. Well, let me see if I can open this a different way. And then we'll have to swap. Oh, I don't want to do that. I will do this instead and move things. Sorry about this. Sure. Oh yeah. Okay. Getting there. Here, I'm gonna have to share a different. Here, we'll share this one. Aha. Okay. Now. Ooh, okay. All right. Can everybody still see? Okay, good. Where are we? Down here somewhere. Ah, okay. So
much, I guess.
I think here we are. All right,
Yes.
that's where we're good. Okay, so as I sort of said, the strictification theorems, you just sort of assume that that a bunch of things are the identity, and that often allows you to bypass some kind of stickiness in the middle of a computation. On the other hand, if you are in a position where you actually just need to work with a specific monoidal structure, you don't want to change from the category of sets with the Cartesian product to some equivalent version, you actually care about sets, well, that's when you need to use one of these diagrammatic theorems. Okay, so keep all that in mind, and we'll have a quick rundown of two-monad theory, and then we'll come back to how this all applies. So a two-monad, jokingly, is what you get when you take the definition of a monad and you just put two in front of everything. This is essentially true, and I want you to think that a two-monad is basically not that much more complicated than a monad. So you got a two-category K. You should just think that that's cat with categories, functors, and natural transformations. Let's just always assume K is cat for this talk. You have a two-functor T from K to K. This is the thing that's going to tell you what kind of algebra. And then two natural transformations, mu and eta, of the same form that you would have if we were dealing with an ordinary monad. And the axioms are, in fact, exactly the same axioms that you would get for an ordinary monad. And the idea here, for this talk especially, is that structures on sets are described by monads. So structures on categories are going to be described by two monads. So something like there's a two monad whose algebras are monoidal categories. There's a two monad whose algebras are categories with products. We won't worry about any of the kind of too technical details about this. But the algebras are also given in exactly the same way that the algebras for a monad are given. So an algebra for T is going to consist of an object X in your two-category K, and then a one cell, which I'll write as little x from Tx to X, and it satisfies the same axioms as algebras for a monad. Now, the new thing is going to be not at the level of algebras, but at the level of morphisms. I should say that there is a more general notion of a pseudo-algebra over a two-monad. I'm just not interested in them right now. So a pseudomorphism between a pair of T algebras is going to be a one cell between the underlying objects, and then normally an algebra morphism for a monad would have a commuting square as an axiom. So the outside of this square would commute. But for a pseudomorphism and a two monad, we have a two cell isomorphism, and then there are going to be two axioms. And we say that a pseudomorphism is strict if this F bullet is the identity. In other words, it's just a morphism between algebras in the usual monad sense. So how do people talk about two monads and these coherence theorems? The kind of classical approach to this, going back to work of, say, Blackwell, Kelly, and Power, really starts with this idea of a pseudomorphism classifier. So a pseudomorphism classifier for a T algebra is another T algebra that I'll call QX, because I want to think that this is like a cofibrant replacement for X, and a pseudomorphism zeta from X to QX, such that composition with zeta gives a bijection between pseudomorphisms from X to Y and strict morphisms from QX to Y. And this needs to be two natural in Y. In other words, given the filled in parts of this triangle, so for all pseudomorphisms along the bottom, the pseudomorphism zeta along the left diagonal, there exists a unique F tilde, which is going to be a strict morphism from QX to Y. This is the idea of a pseudomorphism classifier. And two monadic versions of coherence theorems often kind of have this sort of format. I'll say first, every T algebra has a pseudomorphism classifier, and the assignment from X to QX is a two functor with the property that zeta, so that's this pseudomorphism from X to QX, is a two natural equivalence. So it's a two natural transformation, first of all, and all the components are equivalences. There are stronger versions of this. So this kind of sketch version that I've given really is like more like what you would find in Blackwell, Kelly, Power, or maybe John Power's general coherence theorem paper. But if you go look in Steve Lack's codescent and coherence paper, you would get a version of this where it not only applies to algebras like we're dealing with here, but also pseudo algebras. Once again, I'm not interested in kind of that level of additional detail. So I just want to convince you first that this is really just an adjunction. This is really just an adjunction. And the way we express this adjunction is by first saying, well, there are two different two categories whose objects are T algebras. There's T alg S, so the objects are going to be T algebras, and the morphisms are going to be the strict T algebra morphisms. And then there's a notion of two cell, which is essentially the same thing as like a monoidal transformation, but we won't really need to worry about those. And there's a two category T alg P, whose objects are T algebras, and the morphisms are the pseudomorphisms as I defined earlier. And there's an inclusion I from T alg S into T alg P, because every strict T algebra morphism is in particular a kind of pseudomorphism. And then the pseudomorphism classifier Q is just the left adjoint to I. That filling in the triangle is a classic, if there exists a unique filler, then something is a left adjoint. And in this case, strict morphisms from QX to Y are in bijection with pseudomorphisms from X to IY. I doesn't do anything on objects because T alg S and T alg P have the same objects. And then the coherence theorem is this adjunction exists, and the unit of this adjunction is a pointwise equivalence. So that's what I would describe as like the classical approach to coherence using two monads. And now I want to talk about this other slightly less well-known approach that I learned from Joyal and Street. Okay, and it starts with this idea of a universal pseudomorphism. This is a complicated definition, but I'll try to give you a feel for what it means and how to use it. So we've got K. This is a two category, and it's got a two monad T on it. We're going to start with a one cell in K. So this is like a functor between categories. And we're interested in, say, monoidal categories or symmetric monoidal categories. And so a universal pseudomorphism for this one cell phi from C to C prime in K is, well, if it's going to be a universal pseudomorphism, it should first of all be a pseudomorphism called phi tilde. And it's going to go from TC, so that's the free algebra generated by C, to something that I've written T of C prime comma phi, which we do not know yet. This is a new object, such that, and this is the universal part, given any other pseudomorphism F from an algebra X to an algebra X prime. Remember, C and C prime are just objects in the two category. They're not algebras for the monad, the two monad T. So given a pseudomorphism F, and one cells R and S, making the outside of this square commute. So along the bottom, we've got the underlying one cell of the pseudomorphism F. So U is going to be, just take the underlying one cell. So we've got phi along the top, R and S along the sides, and F along the bottom. Given that, there exists a unique pair of strict morphisms, R bar and S bar, making all of the pieces of this commute in the appropriate places. So R bar goes from the algebra TC to the algebra X, and the triangle on the left needs to commute in the two category K. Now, TC is the free thing generated by C, the free T algebra. So R bar is just the usual thing that you get from R out of the free forgetful adjunction that T gives you. On the right, we've got an S bar, and it's going to go from TC prime comma phi to X prime. This is another strict T algebra morphism. And then we have a little triangle. That triangle also commutes in K. Now, this one, we can't really understand very well because it's got this kappa sub phi. This is going to be something like a unit, but since we don't know what T of C prime comma phi is, we can't really say much about what kappa phi is, and therefore we can't really say much about what S bar is. So this is a bit of a mystery at this point. The top rectangle also commutes.
Sorry, what's U here?
U is the forgetful functor from T algebras to K.
Ah, okay.
Okay, so the top also commutes just in K, and you should think that the top rectangle says that this kappa sub phi, in some sense, kind of extends the unit eta from C prime to TC prime, except that this TC prime doesn't appear in this diagram. So this T of C prime comma phi is going to be something that's like TC prime, but more complicated. And then the bottom rectangle is going to commute in the two category of T alg P. So if we remove all the U's, then we get T algebras and pseudomorphisms between them. Phi tilde is a pseudomorphism. S bar is a strict morphism, but in particular also a pseudomorphism. And that's going to be equal to R bar followed by F as pseudomorphisms. So this is the definition of a universal pseudomorphism. Let me try to convince you that this is a reasonable thing. So first of all, what this is trying to do is freely generate morphisms that are not strict. So what do I mean by that? Well, if you've got a monad or a two monad, you can always use it to make a new one on the arrow category, or in this case, the arrow 2 category, by just applying your monad to arrows. So you get a new monad T lower star on arrows of C, where T lower star applied to a one cell phi from C to C prime is just T phi from TC to TC prime. Now, the morphisms in the arrow category are commuting squares, and the unit for T lower star is just the naturality square for the unit of T. In other words, the unit at the object phi is this square here where we have phi composed with eta is equal to eta composed with T phi. And T phi, since this is the unit morphism, T phi has a universal property. So it's the universal strict T algebra map generated by phi. In other words, if I had a different commuting square with a strict T algebra map along the bottom, I would get a unique factorization in the arrow category. That is very similar to what's going on with the universal pseudomorphism. So at the bottom here, we have the strict version. So I've got a top rectangular region, which is a unit naturality square. And then I've got a pair of arrows to a strict T algebra morphism. And if the outside square commutes, then I get a unique pair R bar and S bar, which are going to be T algebra morphisms, making all of these regions commute. And the universal pseudomorphism is doing the same thing, except now we've got pseudomorphisms along the bottom, and the thing that it makes, instead of being T phi, is this phi tilde, and it's going to be a pseudomorphism. This also hopefully illustrates the sense in which this kappa map is kind of like a unit. It's just a more complicated unit because the object TC prime comma phi has more stuff in it than the object TC prime. I'll give you some explicit formulas later, and you'll get to see just what else it has. So this is what the universal pseudomorphism is trying to do. It's trying to freely generate some pseudomorphisms with a universal property in a kind of arrow category theoretic fashion. Okay, so let me get to some theorems that Niles and I proved. So the first one is that there's an induced strict morphism from TC prime comma phi to TC prime, and it's an equivalence. Here is how you get it. You just apply the universal property of the universal pseudomorphism to the square, which is the naturality square for the unit. That's what's going along the outside. You've got the unit for C, the unit for C prime, and you've got phi. And then along the bottom, you've got T phi, or U of T phi. T phi is a strict T algebra morphism. In particular, it's therefore also a pseudo T algebra morphism. The kind of little diagonal dashed lines on the left by the universality of eta, you just get the identity. And then on the right, you get, well, something. And the one on the right is the strict morphism that we're looking for. So this is how you get it. I'm not going to go into how you prove that it's an equivalence. This is some diagram chasing. It takes a little bit of effort. So why is this a coherence theorem? And the reason is because TC prime comma phi has diagrams like this one that I had at the beginning of the talk, with homology being applied to various things, either with tensors between the homology or the homology of a Cartesian product. We've got these Eilenberg-Zilbert comparison maps, and we've got a variety of symmetries, both in the category of topological spaces, where we've applied homology to it, or in the category of graded abelian, graded vector spaces, I suppose this was. So this is exactly the kind of diagram that lives in TC prime comma phi. So I'm going to use this theorem that there's a comparison between TC prime comma phi and TC prime that's an equivalence to understand diagrams like this. Before I do that, I want to relate this back to these pseudomorphism classifier approaches to two-monadic coherence. These seem somewhat similar, but it's not necessarily obvious how similar they are. So Niles and I proved two theorems. The first is that if T has appropriate pseudomorphism classifiers and the category of T algebra has some pushouts, then T also has universal pseudomorphisms. So the idea for this is that if I want to construct the universal pseudomorphism generated by a morphism phi, I'm going to take the pushout of zeta from TC to QTC. Remember, the assumption here is that I've got pseudomorphism classifiers. So I've got this zeta and this QTC. I'm going to take the push out of that and T phi from TC to TC prime. This push out construction is extremely useful when you're doing an actual example. And that topological space, graded vector space example, the way I know how to do it is by using this push out. Now, there's a little bit more work that goes on here, because actually I can't take the push out of these two things as written. I've got to replace zeta with a strict version of zeta, and then do a bit more kind of back and forth to get things in the right spot. But this is the main idea. So the second thing we proved is that if T has universal pseudomorphisms and the category of T algebras has some coequalizers this time, then T has pseudomorphism classifiers. The idea here is that the universal pseudomorphism generated by an identity has the universal property of QTC. So the pseudomorphism classifier of the free algebra on C. So then if you have an arbitrary algebra, you can express it as a coequalizer of free algebras. And this Q is supposed to be a left adjoint. So in particular, it should preserve any coequalizer that exists. So you define Q for an arbitrary algebra as a coequalizer of Q of the free algebra, which you get through the universal pseudomorphisms. That's the basic idea for the other way. So in some ways, having these universal pseudomorphisms is about the same strength of hypothesis as having pseudomorphism classifiers. Now, both of these things are easy to make if your categories have lots of colimits. So you should think of these as being weaker assumptions than having like co-complete and say finitary monads or something like that. Okay, now I want to spend the rest of the talk getting back to symmetric monoidal categories and talking about how you would use these theorems to actually check a diagram. And for that, I need to tell you what TC prime comma phi looks like in a specific case. So T is going to be the two monad, and I'm just going to take strictly associative and strictly unital symmetric monoidal categories. This is just so I don't have to worry about any kind of parenthesization or something like that. So if I've got a functor, so T is a two monad on cat. So I've got a functor phi from a category C to another category C prime. I need to tell you what the category T of C prime comma phi looks like. And here is a kind of basic description. So the objects of TC prime comma phi are finite lists where each element in the list is either an object of C prime, so it's an object in the target, or it's a new symbol, phi of a list, where the list inside the phi is not allowed to be length 1. If it's length 1, then it's already an object in C prime. And then the elements of that list are objects of the source. So you can have a list, and in that list, you either have objects of the target or you have a new thing, which is phi of a bunch of things in the source. The morphisms are generated by, well, we need the morphisms of both C and C prime. So the morphisms of C act on the things in the new kind of phi symbols. The morphisms of C prime are allowed to act on the objects in your lists, which are in C prime. Then you need symmetries. You need the symmetries of objects in the list inside the phis. You also need the symmetries on the whole list. And you need some isomorphisms. The main ones are isomorphisms that say if you have a list and you have phi of something as one term, and then the next term is phi of something else, you're allowed to make that into one big phi of a large list of things in C. And also, while my lists inside the phis are not allowed to be length 1, we need this sort of condition where phi of the empty list is isomorphic to the empty list. And of course, there have to be some axioms telling you how these things work. The list is somewhat long, but none of them are surprising. And in fact, you're much more likely to write down a redundant set of axioms for the structure rather than miss some important ones. Okay. So let's go back to this diagram. We've got this complicated thing, and now I want to apply my map from TC prime comma phi to TC prime. And what do I get? Well, I get this thing on the bottom. So TC prime, the objects are just lists of objects of C prime. And what this map does is it doesn't know the difference between HX tensor HX and H of X cross X. So in red, I've highlighted all the things that the map from TC prime comma phi to TC prime, all the things it changes. So in particular, it changes that Eilenberg-Zilber map along the top to an identity. The one on the left also to an identity. It doesn't change any of the permutations, but you can see that the permutation in the bottom left used to be inside a homology functor, but the mapped from TC prime comma phi to TC prime just gets rid of that homology functor and treats it as a permutation of those objects. This is a much easier diagram to check because all of the objects are the same. So we just have two automorphisms of the triple tensor product of the homology of X. And each one is just given by a symmetry. And that means all I have to do is decide what elements of S3 these are. And it's straightforward to check that they're equal. So this diagram commutes. The reason that the original diagram commutes is that this map from TC prime comma phi to TC prime is an equivalence. So if I check the map in TC prime, if I check the diagram in TC prime, it commutes there. I can go backwards along my equivalence and conclude that the original diagram commuted. That's how you might use this to check an actual diagram. So here is another sort of more general example that you can think about. So here, T will be, we can do either braided or symmetric monoidal categories. And for a while, those two monads will, the story will be the same. I've got a braided or symmetric monoidal functor F. Once again, I've written down kind of all the appropriate data and axioms that we need. So we've got an isomorphism F2, which has a component FA bullet FB is isomorphic to F of A plus B. And so a question you might ask yourself is F2 itself a monoidal transformation? And this is the diagram that you would have to check. And you can do this by hand. There's no coherence theorem that you can come up with where you kind of can use it, but then not check the diagram by hand. The question is always, how much easier does the coherence theorem make it? And so now in this case, if we use this map from TC prime comma F to TC prime, we get the diagram at the bottom. So we've changed all of these isomorphism F2s. They get changed into the identity because this map from TC prime comma F to TC prime doesn't know the difference between F of A plus B and F of A bullet FB. The diagram at the bottom just obviously commutes. We've got a bunch of identities, and then the only two other morphisms are 1 beta 1 in black on the left, and then 1 beta 1 in red on the bottom right. And those are visibly the same. So we can use this theorem to conclude that this map F2, this isomorphism that we got from the braided monoidal structure or symmetric monoidal structure on a functor F, is always itself a monoidal transformation. Now, I put a little asterisk here because once again, I've slightly obscured a little bit of what's going on. So I should say that, first of all, this is not actually the map that you want to do. You want to do a version of this that only uses the objects of C and C prime. This is not a particularly interesting or complicated kind of change. But I should say that the way to go from the image of this diagram commutes back to the original diagram commutes, that uses conditions similar to coherence for monoidal categories. In other words, I told you in a monoidal category, people say that every diagram of associativity and unit isomorphisms commutes. Well, that's not quite right. That's only true if your diagram comes from a diagram in a free one. And it's exactly the same kind of thing here. So I picked a diagram that this strategy works for, but there are other diagrams where it's easy to check that it doesn't work. Now, we've used this to conclude that F2 is a monoidal transformation. And this is, for me, particularly interesting because it does not depend on the underlying braid or permutation of F2. So you might think, well, what does that mean? So some monoidal functors, the isomorphism F2 is itself a combination of braids or symmetries. So one of the examples that I was particularly interested in is if you've got a monoidal category, a symmetric monoidal category, there's a symmetric monoidal endofunctor, which is multiplication by 2. In other words, it sends A to A plus A. You can do this for any natural number that you like. There's a multiplication by n symmetric monoidal functor. And the F2 that you have there has a non-trivial underlying permutation. But if we go back to what happens when we apply this map from TC prime comma F to TC prime, you can see there aren't any more F2s. That doesn't mean that F2 doesn't contribute something, but what it does mean is that if F2 did involve a symmetry or a braid, then the net contribution of those would be zero, even though F2 itself maybe has an underlying complicated braid or permutation. So as I said before, this came about by thinking on how to extend ideas from the sort of ordinary algebra of abelian groups to symmetric monoidal categories. And one of the topics that Niles and I were interested in was something like, well, if I have some free abelian groups and group homomorphisms between them, those are just matrices with integer values. What happens if I think of these as symmetric monoidal categories? Do I get to do the same kind of computations that I'm used to from the ordinary linear algebra that you get in abelian groups? Does that still work when you go to the world of symmetric monoidal categories? And it turns out that often the answer is yes, but not in such a straightforward way. You have to use some kind of additional coherence technology in order to make the same kinds of conclusions. That is all I wanted to say. Thank you very much.
Well, we thank you very much.
Does
So
anybody...
any questions or comments?
Is there something in the... Oh, okay. So there's something in the chat. For the coherence theorem you mentioned at the beginning, is theorem 2, every diagram commutes under the condition of freeness, satisfied in higher dimensional categories, especially for structures larger than 2-dimensional categories? Are stronger structures required for 3 categories? For example, the model category of 3 categories. That's fine. Yeah, thanks for the question. So in the specific case of 3-dimensional structures, I can tell you that all of these conditions still work. So this was a thing that I studied in my thesis, actually, that if you take a 3-globular set and you can freely generate a strict 3 category from it, or you could generate a tri-category from it, or in the middle, you could freely generate a gray category, and there are canonical maps between all of those things, and all of those maps are tri-equivalences. So in the free structure, the sort of most complicated thing you could write down is a tri-category, and it's got exactly the same commutativity properties that you would get in a strict thing. So nothing, as far as I can tell, would change in kind of higher dimensional but finite categories. So weak n categories, not in the infinity comma n sense, but in the sort of n globular set sense. I think you would expect this to still be true, that diagrams that come from free things should commute. Very welcome. Anybody else have a question?
May I ask you about, so you talked about symmetric monoidal categories and their like the generalization to 2 monads. Can you formulate, so I know that in a symmetric monoidal category, there is a generalization to a braided monoidal categories. And also there are several developments towards pentaganator and other stuff. So can it be somehow translated into 2 monads language?
So the way that like the way that a lot of these things work is the particular algebra that you're interested in. So in this case, if you're interested in symmetric monoidal categories, there's a 2-monad whose algebras are symmetric monoidal categories. And it's the two monad that like builds in all the structure. So if you want to move to a higher dimensional structure, so instead of symmetric monoidal categories, you want, say, like a symmetric monoidal 2 category, then you would need a higher dimensional monad. It turns out that this doesn't seem to work as well as people want. So you can do things in a very, very weak sense, but they're hard to kind of compute with, and the definitions are extremely long. This is why people study things like gray categories and these kind of semi-strict notions where you don't have as many coherent cells as you would for a general thing, but it also models the general case well. But the kind of two monads approach, this is a very peculiar thing about dimension 2, is that you can reduce so many questions to questions in enriched category theory. This doesn't seem to work quite so well in dimension 3. So all the structure is like somehow in the two monad. And then if you want to generalize that, you have to generalize two monads. That seems to be the hardest step.
So maybe I will ask one question from Langland's program point of view. There is this notion of Tanakian categories where they're equivalent to the representation theory of certain pro-algebraic groups, for example. So this symmetric monoidal categories, they are kind of Tanakian category, I guess, but without a fiber functor, I guess, right?
So in general, they're not going to be Tanakian. I'm sure that many instances, maybe the right thing to say is that often the Tanakian ones are symmetric monoidal, but a
Right.
general symmetric monoidal one, won't have a fiber functor, won't be representations in any meaningful sense.
So there is no such Tanaka duality kind of theorem in this generality, I guess.
No, not at this level of generality. These are too broad.
Okay, yeah. Thank you very much. I guess there is one more question, maybe.
Oh.
Oh, that's thank you message. Yeah.
Anybody else?
So then let's thank our speaker once more. Thank you very much, Nick.
Yeah, thank you.
In general, we meet once in 2 weeks' time, but this time our next seminar will be 3 weeks from now, and Will Donovan from Beijing, he will be speaking. So